we arrive at our last special equation, but it's not actually an equation, it's an inequality. It still has the same flavor. You're trying to solve it. But the first thing and the main thing is to realize we're talking about something that is greater than, well, as you can see from this example, greater than 0. It doesn't have to be greater than 0, but it's an inequality. And how do we solve this kind of problem? Well, I know you have had exposure to greater than and less than, and I expect you to understand all those things. Like if you divide by a negative, you switch the sign, and yes, you know about number lines. But actually, I'm going to show you kind of an interesting, probably new way to use a number line, and I'm not talking about just giving your answer. So this is definitely more of a higher level, getting you ready for calculus kind of problem. But you can do it. You won't say it's the hardest thing ever, but it's kind of a new approach. Now, what do you think? 2x squared minus 3x minus 20. Do you realize, I've actually done this for some other problems this year, but I want you to start to realize as a math student that any expression, I want to be careful not to use the word equation, but technically any expression can be thought of as a graph. There's a graph of 2x squared minus 3x minus 20. And the reality is any expression can be a graph. You say, how? Well, I just kind of have to pretend that it's like y equals. But if you think about it, now that I'm trying to get you to think about it, what would a graph say about 2x squared minus 3x minus 20 being greater than 0? Seriously, think about that for a moment. How would a graph say that 2x squared minus 3x minus 20 is greater than 0? Let's find out. This is like a visual thing. You can look up here if you want. You can play along on your own calculator. Now, it might not be a huge surprise, but maybe you weren't thinking about it before I did it. That's a parabola. That's a parabola. And a lot of times when we have a graph up on the calculator, we just interpret it with a simple sketch. Never a bad idea. But I go back again to kind of my original question. When is the graph greater than 0? Where do your eyes see the graph being greater than 0? You want to be thinking of that. You want to be seeing that as this part of the graph, as it's greater than 0, and this part of the graph, as it is greater than 0. When the teacher says, when the problem says, when it's the graph greater than 0, that really means one of the y values greater than 0, because the graph really is the y values. Now, just to sort of set the record straight, those yellow numbers, those yellow x values, those are the answers. And for those of you that are like, what are the answers? Well, we're about ready to find them. But there's something bigger going on here, and that is that the place where these answers seem to start or stop have everything to do with these x-intercepts. That won't be the last time you hear that. So again, the place where these answers start or stop have to do with the x-intercepts. So finding those x-intercepts would probably be a good idea. Now, I already wheeled my calculator away, but maybe you can see from yours, or just trust me, that this x-intercept was at -2.5 from the graph, and this one was at 4, again, just by looking at the graph. So can we write some solutions by using the graph? I think we can. These x values that are in yellow are to the left of -2.5. So we can say x's that are less than. And these x values over here that are in yellow, they're to the right of 4. So we can say greater than 4. But there's a little more to this. You see, this graphing method was to get us to realize that, well, that the x-intercepts are literally critical. In math, when we use the word critical, that doesn't just mean like super important. It actually means a place where things change. You'll hear this many times again in calculus next year. It's not a hard idea, but it might be a new way to think about x-intercepts being a place of change. And they're the place where the function will always change from positive to negative or negative to positive. And what I want to do is explore with you a way that we can think about all this. That is x-intercepts, that is positive and negative. That we can think about this without using a graph. Because as a lot of things tend in here, we try to move away from using a calculator. So I want to kind of, I don't want to say do a different approach, but I want to do an approach that doesn't require a graph. So how do you find x-intercepts? Well, the good news is it's something that we've been doing a lot of. Maybe this is where you kind of make that connection that an x-intercept is, of course, when an equation is equal to 0. And I know that you've heard me say that, and you've worked with it a lot. Equations equal to 0 can be solved with all the tools that we've been exploring. I'm going to encourage us to use a factoring tool. But again, you might have used a quadratic formula, and you know the routine here. But it does factor. And I know students, they get a little worried when the leading coefficient's larger, and how do I do this? How do I do it? Again, the Mr. Naylor method is to do a little guessing and checking with 20. Numbers that multiply to be 20 are probably like 20s and 1s, 10s and 2s, or 5s and 4s. Now, that's quite a bit to choose from, but if you do a little bit of looking into the future, the number that you put out here is going to get affected by 2. It's going to get doubled. And the number I put right here is not. It's going to just get multiplied by x. I'm trying to get to -3. Okay, now if you put a 4 out here, you should see that you get an 8. That is an 8x. If you put a 5 right here, because that's what would have to match with 4, that's going to give you a 5x. And, well, 5x's and 8x's can become -3x's if the correct one is negative. Again, that's kind of the Mr. Naylor method. It's really the British method simplified. If you want to use it, you're more than welcome. You don't even need to give me any credit. Make sure the 4 is the negative because you want the 8 to be the negative. Okay, but do you realize that what I'm really doing is trying to find the x-intercepts? And yes, they're going to be the same. They're going to be x equals -5/2, which is actually that -2.5, obviously in fraction form, and then x equals 4. Now, stick with me because I don't want you to say, well, it's kind of the same thing you already did. Well, yeah, it is kind of the same thing I already did. I found the x-intercepts, but here's kind of the big idea. It's the big idea for this entire topic. We can take these x-intercepts and we can put them on a number line because, well, we know that they are going to be the critical numbers. They're going to be the place where things change. And so what we're really doing is we're putting these critical points on a number line and kind of dividing numbers into 3 regions. The region to the left of -5/2, the region in between -5/2 and 4, and then the region to the right. What do I mean dividing into regions? Well, you can take any number you want in this region and you can test it. You can check it. You can see what kind of value comes out. Just go with this with me. A number that's to the left of -5/2. Okay, the closest one that's easy to use would be like -3. Now what I can do is I can test that number. What do I mean? Well, I can plug it back in to my inequality. Now my inequality says that it's always going to be 2x squared minus 3 times x minus 20. It's a little fancy. You should be able to do this math without a calculator. If you just kind of play along with me here, we're going to get like 18, because that's 9 times 2, so we're going to get 18. 18 plus 9 minus 20. 18 plus 9 minus 20. Okay, well, I'm pretty sure that comes out to be 7. Right, 7. But as you'll find out, what I really am concerned about is that it came out to be positive. What I'm really concerned about is that it came out to be positive. And you'll see that I'm noting that in that region. I'm putting a plus sign. Because what that means is that every number on this side of negative 5 halves is always going to give a positive output. If you're looking at this graph, you should be saying, yeah, that's kind of what we discovered with the graph, but I can do this with this number line. Wonder what number we could pick that's between negative 5 halves and 4. Well, if you can pick 0, usually you want to. If you can pick 0, usually you want to, because it's very easy usually to plug in 0. In fact, you don't have to show all this work. I just want to make sure you realize what I'm doing. I'm plugging 0 in, and well, of course, 0 squared minus 3 times negative 20 every time. What I'm really concerned about is that it came out negative. And we have one more space to check. It's actually an interval. You can pick any number you want to the right of 4. Most people would pick 5 just because it's small and simple. And if you plug in 5, I'm going to just save a step here and just tell us that we get 15. We get 15. What I'm really concerned about is that it came out positive. Now remember, I want you to look at this number line and realize it's the same as this graph. But I also want you to realize that we're going to take the graph away really for the rest of these problems. So what does this number line say to us? Well, it says what kinds of positive and negative outputs we're going to get based on the interval. And since I want to be greater than 0, then I want to be grabbing the positive outputs. Oh, to the left of negative 5 halves. The positive outputs. Oh, to the right of 4. And so when it comes to my final solution, yes, it's the same answer. I'm going to write it as an interval just to kind of give us a different perspective. But I'm grabbing the spaces, I'm grabbing the intervals that are greater than 0. It's a number line approach. And it works because we know that the x-intercepts, now listen to this, are the only places where something could change from positive to negative. Again, you don't have to worry that there's some other number in here that's going to give us a positive or negative change. It's always going to be these critical points, the x-intercepts.
Would you rather us have it like an inequality, or would you rather us have it?
Yeah, I really would say the answer to that is that you should understand both. And I'm pretty sure there's never a time where I say must. I never say must. So if you're kind of an inequality student, if you're more of like an interval, I'll probably mix and match both. If it's a multiple choice test, you should be able to recognize either one. I want to do one more with you, and then we'll just kind of draw a line and stop. But it's nice to see two. Oh, before I do that though, here, let me present this. This would be helpful. It's kind of the method that we've done. As I usually say, do what you want with this, read it, write it. There is something in this first step though that might catch your attention, and it's the other little piece of the puzzle. It says that you want to solve the equation equal to 0 or undefined. That's important. I hope to show you, but notice please, the equation should be solved equal to 0 or undefined. And maybe it should say and or, because there is a time where it could be both. I'll show you that in the next problem. It just gives more critical points. So we put these on a number line. I would imagine it's going to become pretty natural for you. you put them on a number line. Don't think that the number line is somehow childish. It's actually a very sophisticated way to organize your thinking. So we put the critical values on a number line. Those, of course, would be those x-intercepts. You do some evaluating. Some people will do that in their head. I will demonstrate that idea of doing some quick evaluating for positive and negative. Let me encourage you not to go to a calculator so quickly to plug numbers in. We want to try to be thinking about how to do this without a calculator. And then you have to kind of like make your conclusion. Your conclusion is to decide what the number line says. Does the number line say these numbers are positive, or does it say that these numbers are negative? 2x minus 6 all over x minus 5 is to be solved less than or equal to 0. I know it's pretty obvious right now. We're sitting here engaging, but the first thing you do want to notice is that it's an inequality. Okay, when these problems are all mixed up on a test or quiz, that's important, okay? Because as soon as you see the less than, greater than, you want to think critical values, number lines. Okay, in this case, equation equal to 0 or undefined. Undefined is definitely a fraction and brings up that possibility of undefined. Now listen, the only time that a fraction can equal 0, at least a simple fraction, is when the numerator is equal to 0. So we have ourselves a little equation to solve. When does the numerator equal 0? Again, that's the only time when the whole thing can equal 0. Make sure that you conclude that that would be when x equals 3. It's probably something you can just kind of conclude mentally. Now, it tends that people don't do what I'm doing. That is that they then jump to the number line. But the reason that I'm doing this is because I want to make sure we don't forget that x equals 3 is going to go on the number line. It is a critical value. We found it so quickly, but it's definitely a critical value. But it's going to have a friend come along, because a fraction can be undefined. Now, when is a fraction undefined? Well, when the bottom is equal to 0. It turns out that that also will make a critical value. I didn't really show that to you graphically, but the bottom line is a number that makes the equation undefined, of course, x equals 5, is also a critical value. So it goes on the number line. I'm going to cheat a little bit here because I thought we were going to have a negative number. I just want to make my number line balance. So I'm actually going to put the 5 there and the 3 there. Here's what you want to realize. This inequality will only ever change from positive to negative at these two numbers. That means that you can be totally confident to check out any number over here. 0. Now, if you're like, oh, I was going to use 2, that's fine. You can use 2. But I just want to show you how plugging in 0 probably mentally is pretty quick. Because if I plug in a 0 to this whole equation, you just get -6 and -5. Okay, so it's usually pretty easy to do. -6 over -5. Well, listen, all we really care about is that that's positive. That's positive. So maybe you feel like that you want to do a little bit of this on your own. I would suggest that you plug in 4. Make sure you're plugging into the entire fraction. So you should feel like you're getting And that will be okay. So I don't really care how much you show here. Right? There will be students that do all this mentally. Be careful. We'll get into some problems that are quite a bit more fancy, but it's all about positive and negative. And if you plug in 6, you get 12 minus 6, which is 6, over 6 minus 5, which is 1. Again, pretty easy to say positive. Let me share right now, because sometimes people will wonder, is it always going to change, positive, negative, positive, is always going to like change? Not necessarily. It's interesting, a critical point is just a potential place for change. Now, it's common to change, if this is positive, then this is going to be negative. That's common, but there will be some problems you do where you get a positive and then another positive, because actually a critical point is just a potential place for change. I'm sure you've seen some x-intercepts where the graph doesn't change, right? Touch, it would come down and touch, but it wouldn't change. So there's always that possibility. We'll see some of that next week. But what do we need? What do we need? We need numbers that are less than 0. This is important. This is kind of step 4. You have to say, oh, I need the negatives this time, because I need to be, okay, so, negatives, between 3 and 5. Between 3 and 5. But I hope you wrote that in pencil, because there's something, it's a small thing, but it'll be the last thing we say. There's something about the way I wrote this answer that's not 100% right. It doesn't have to do with, that I didn't use inequalities. It actually is something a little more mathematical. It does say less than or equal to 0. We all know that equal to means that we should include the numbers. So we should include 3 and 5. But unfortunately, one of these numbers can't be included as hard as we try. One of these numbers can't be included. It's the one that makes the denominator equal 0. It was there as a critical value, but it can't be included as the overall solution. Okay, because at x equals 5, we still are undefined. We're undefined. So, sorry, 5, but thank you for still being our endpoint. We just can't include you. Okay, that's just a little detail because it was a fraction. And we will, again, do a little more of that. But I wanted to expose you to as much as possible. Any thoughts?